Yeah, let's just start this equation. And this Hamiltonian is that when you're applying magnetic field, and the Hamiltonian can be changed under the Lorentz gauge and also the first term gives rise to the paramagnetism, and second term describes the diamagnetism. In here, then let's firstly consider for the diamagnetic term, and also here diamagnetism term is that like this, yeah. And diamagnetism. What is the diamagnetism? Diamagnetism means that negative magnetic susceptibility. We already know that the magnetic susceptibility is the m over h by applying magnetic field. And anyway, this is h field direction, and usually the magnetism should have the point parallel to the field direction in many cases, but in some cases, and they do not prefer the parallel direction, but different negative direction may have. In this case, the negative value for magnetization, and therefore the negative magnetization means that it is negative magnetic susceptibility. It is the Lenz law. The reason why the negative magnetic susceptibility is due to the Lenz law. Anyway, as I discussed previously, when you apply magnetic field in the sample, increase the magnetic field energy, and in nature they do not favor to increase the energy. They'd like to have the ground state with the lowering energy, and in order to have the low energy, and they behave like that, expel the applying magnetic field that generates the negative magnetization, and that is the reason why they have the diamagnetic moment. Here, when we see that in the Hamiltonian in this case, and they have the angular momentum and spin angular momentum, orbital angular momentum and spin angular momentum, and we will discuss for the angular momentum later as like Hund coupling. And but for example, in the case L equal 2, there are 5 different orbitals: 2, 1, 0, -1, -2. Also, in each orbital, they can occupy the 2 spin state from the Pauli exclusion principle, as at a single orbital, 2 electrons can occupy. When you think about that, full occupation of the orbital, in this case, total angular momentum is that 2, 1, 0, -1, -2, and the summation of all the angular momentum equal to 0. And in the spin case, is a spin up and spin down is a spin 0, 0, 0, 0, 0, and total spin also 0. Therefore, in the case of the fully entire field electronic shell, do not have the paramagnetism term, because the 0 orbital angular momentum and the spin angular momentum. Therefore, in the diamagnetism is significant in the case of the entirely filled electronic shell, totally occupied shell in the entirely occupied orbital of the shell. The paramagnetic term equal to 0. Therefore, just only the diamagnetic term should be employed. And also, let's consider for the magnetic field. We apply magnetic field along the C direction, 0, 0, B. In that case, and let's consider for the B cross Li. and from the definition, ijk and b 00b xi yi gi. Then in here, the b case is that the minus I byi plus jbxi. Therefore, b cross ri square is that b square xi square plus yi square. Therefore, this diamagnetic term may have the e square b square over 8m and xi square plus yi square. It is a for summation for I. It is a diamagnetic term. And also basically this diamagnetic term is very small by comparing with zero field Hamiltonian. In the case for zero field Hamiltonian, H0 is a zero field Hamiltonian, and this diamagnetic term is very small quantity, H prime. In this case, we can use that perturbation theory. Perturbation theory in quantum mechanics. Therefore, let's consider for the perturbation, let's employ the perturbation theory to calculate the diamagnetic term. In the let's denote that H0 plus lambda V, and here lambda is a parameter for small Hamiltonian, small, and V is the small interaction. And also from the Schrödinger equation, the eigenstate of the Schrödinger equation, the eigenvalue problem is that Hn equal to Enn. Here n is a state and En is the eigenvalue of the problem. It is a Schrödinger equation. And in this case, let's assume that the energy state has the constant energy, 0 point energy plus the first term, lambda, the first perturbation energy and the second perturbation energy, like this. And anyway, here lambda is any parameter. We should define that the lambda, and also the state. Also, let's expand the higher harmonics for the n0 state plus lambda and n1 state plus lambda square and 2 second order. Here, in this case, from the energy, therefore, at the kth order energy is that 1 over k factorial, and k derivative with lambda of the energy En. And also, the n state, kth order of the n state can be represented 1 over k factorial, k derivative with respect to the lambda for n state. Therefore, from the Hamiltonian Schrödinger equation problem, the Hamiltonian is H0 plus lambda V, and also eigenstate can be expanded like n0 plus lambda n1 plus lambda square n2 plus and so on. And it is that energy is that En0 plus lambda En1 plus lambda square En second term, like this. And also eigenstate N0 plus lambda N1 plus lambda N2, like and so on. And here, let's consider for the first order of lambda. First order of lambda term. In here, in this case, and the lambda term can have the H0 N1 plus V N0 V N0 state, and in the energy En0 N1 plus En1 N0 state. It is first order lambda. Let's denote this first equation. Then this is E1 state can be represented by the N0 En1 and N0 because the eigenstate N0 H0 and N1, the off diagonal matrix element is equal to 0. Therefore, it is just only the diagonal term can be expected. Therefore, En1 is that here N0. Let's denote that it is N0 expectation value. N0 expectation value, the first term equal to 0, and Vn0 survives. And also here N1, in this case N0 and N1 matrix element also 0, when we employ the diagonalization, and just only the here. Therefore, we can write down like this. And also, Vn0 state can be represented. Vn0 state is like that. For each k state, but the k is different to A, and K0 V and 0, this is first term, and also plus N0 case N0 V N0. It is k equal to N0 state. Therefore, it is like that. This one is the En1, and therefore it is a summation for k is not equal to n K0 V N0 and plus En1 and N0. Here, let's substitute this one to the equation 1. Therefore, Vn0 like this. Therefore, it is like that. H0 minus En0, and the eigenstate is N1 is common with each other, and also it is that in the right hand side is En1 and also minus V in 0 state. Therefore, from the above, it is that minus summation k equal to not n and K0 V and 0. Yeah, here. Let's suppose that En0 is not degenerate because non-zero value, and it is not degenerate. Suppose that En0 is not degenerated. Then the K0 expectation for K0 and En0 minus H0 and N1 is that En0 minus ek0 and k0 and 1. Yeah, and also it is identical with the k0 and v and 0. Because v is that okay. Here because let's assume that En0 is not equal to ek0, then the N1 state is that summation for k equal to not n from the above relation En0 minus ek0 and here k0 v and 0 and k0. Okay, therefore it is first order eigenstate, and also the first energy. The first energy is that like this. Therefore, let's assume that the first order energy, let's denote that zero energy n0 like that it is a zero state. The energy difference, the first energy shift, the first order shift of energy, write down delta E0 like that, summation for I and the 0 H prime 0, and also the H prime means that diamagnetic Hamiltonian, and E square B square over 8m, summation for I equal to 1 to G, and the ground state, and the xi square plus yi square 0. And in single atom, we can assume that it is a spherically symmetric. Spherically symmetric. Then xi square and yi square is the same, but it is 1/3 Ri square. Ri square, R means that the radial direction, and therefore the energy shift is that E square B square over 8m, and also here xi square plus yi square is 2/3 summation for I equal to 1 to G, and also 0 Ri square 0, like this. Yeah. Therefore, let's consider for the Helmholtz free energy. Helmholtz free energy is that the F is that the E minus the TS. Then anyway, the E is that S dt minus PdV minus MdV with applying magnetic field. Therefore, the F is that S dt minus PdV minus MdV minus TdS minus S dt. Therefore, it is minus PdV minus MdV minus TdS. Therefore, the magnetization can be written down minus partial F, partial B. Here, then the volume and the entropy is a constant. And also, in this case, minus. Here from here, N over V partial E0 partial B. For a solid composed of N ions in a volume V, then in this case, and here, and also there are two spin components, and minus 6m E square B, E square B, N over V, and summation for Li square. Therefore, the magnetic susceptibility chi is that m over h, and it is that, in other words, mu 0 m over b. Therefore, this magnetic susceptibility is that minus n over v e square mu 0 and 6m summation for I equal to 1 to g and Li square. Therefore, it is a negative value. Negative value means that it is a diamagnetism. Usually, the diamagnetism is temperature insensitive, and it is temperature independent. And this diamagnetism is present for all materials, but is very weak because this orbital motion contribution and is very small. When you consider for it is a very small value, and negative value comes from the Lenz law.